Okay. Let me get a new battery for this. Otherwise, it's going to die in the middle of class. Okay, that's weird. For some reason, the microphone is not. Batteries appear to be dead. I'm going to try another one. If at some point in the middle of the class you stop hearing my voice over the speaker, wave. Okay, that's better. All right. So a couple of quick administrative things. If you recall, 1 week from today we have our first midterm. Unfortunately, this particular room is needed by the chemistry department Tuesday afternoon. And so we are moving to a different room just for next Tuesday's review session. It's 217 Noise. It is a slightly smaller room than the one that we're in now. So I do encourage you to show up early. And hopefully there'll be room for everybody, but I unfortunately can't guarantee it. This is the largest room they could find on short notice. This is the main lecture hall for the chemistry department, and they give their annual, they have one talk a year where they invite the equivalent of the Nobel Prize winners to come and tell the University of Illinois all about where chemistry is going for the next 50 years. And it's always in this room on Thursday afternoon. So we're just going to get out of the way. Enough people have signed up now for the conflict exam, and that I can confidently schedule it from Wednesday to 3 to 5. That seems to be consistent with everybody who's signed up for it so far. But the registration form is still live, so if you discover for some reason that you still need to take the conflict exam, don't worry about whether you've heard from me. If you've filled out the form, I assume that you will be coming to the exam. If you change your mind and go to the regular exam, that's fine. We'll just count the pieces of paper after the exams are all over. But I do need to know how many people are going to show up to the conflict exam so I can schedule a room. So please register for this by the end of this week. So if you want to take the conflict, please register for this by this Friday. The other thing that I need to mention, since this is a reasonably large class, this is likely to affect at least one or two of you. If for some reason you need accommodation through DRES, there is likely to be at least one student taking the exam at DRES, but DRES likes to have a week's notice. So if you are planning to do that for some reason, please talk to the people at DRES as soon as possible so that we can coordinate that as well. And if you're in that situation, my recommendation would be to take the exam at DRES on Wednesday, so that you have plenty of time after the review session. There is no homework going out this week because we have the exam. Homework 4 will go out just before the exam and will be due a week later. Homework 3 is due in 4 hours, 5 hours, 4.5 hours, order 1 hours. Soon. Are there any other administrative questions?
Today's lecture won't be on the exam, right?
Today's lecture will not be on the exam. It will be in scope for midterm 2, and of course it will be in scope for the final. But the midterm will cover basically homework 0, 1, 2, and 3, which means prerequisite stuff, a couple of things on dynamic programming, and something treepish or quicksort-ish in randomized algorithms. Okay. So what I want to talk about today is probably the single most abused and single worst understood randomized algorithm or randomized data structure in the computing universe. You've all used these things before. You've all learned strange things behind the barn about how they work. This is hashing. So there's this cultural fiction about the way hashing works, which is that magically you can do constant time membership queries. So you have a set. You can insert things into the set. If you play really nicely, you might even be able to delete things from the set. And you can ask, is this item in the set? And magically, a hash table will tell you yes or no in constant time. Even more general than that, you might attach some information to each of the items in the set. And when you look something up in the hash table, you want this auxiliary information. So a phone book, they don't have phone, actually they still do have phone books, but those of you who have never seen a phone book, it's a book. It has names in it, and next to the names it has your landline numbers. There used to be these things called landlines. But you can think of this as a prototype example of something where you would use a hash table. You hash the name, and the auxiliary information stored in the table is the phone number, or reverse lookup. You hash the phone number, and you get back the name. And somehow, magically, this is all happening in constant time. If you say this a little bit more formally, what you want to imagine is that you've got some universe U of items that you want to store in the table. And I want to map that into a can't spell the word table. Table of size M. And so I have this magical hash function that, let's think of the universe as just being made of integers. And I'll just use U to be the size of the universe. 2, 0, 1, to M minus 1. Okay? I have this so-called hash function. And if I want to find x, the rule is that I will store x at t at the index given by the hash function evaluated at x. Right, so it's very simple. It's very clean. I somehow have to come up with a good hash function, but once I do that, then I know exactly where x is going to be in the table. I just look there. If it isn't there, then, well, I know x isn't in the table, and we're done. Right, this is the 0th order intuition behind hash tables. There's only one problem with this, and it's a big one. Why doesn't this just work? Collisions. Generally speaking, the universe is bigger than the size of the table. The universe is bigger than the table, right? So necessarily, there are going to be multiple items in the universe that hash to the same address in the table. So it doesn't matter what h is. There will be collisions. Okay, by which I mean two items x and y that are different, but the hash values are the same. There is absolutely no way to avoid this, no matter what the function is. And so this simple scheme of just looking at this one address in the hash table isn't going to work because either I need to at least prepare for the possibility of storing more than one thing at that address, in which case I have some extra work to do once I know the hash value, or I have to have some other mechanism for resolving collisions so that the item X is not necessarily stored exactly at address H of X, but some easily computable address nearby. Okay. And now we get into the grungy details. How do you guarantee, given that you don't know in advance which items in the universe you're going to be hashing, that whatever this more complicated collision resolution scheme that you're going to use is, will run in constant time? What a lot of textbooks say is the items you store are random. And if that were true, then it really doesn't much matter what hash function you use. You can use almost any hash function you like. Because the data going into the hash function is random, the hash values coming out will also be random, because applying a function to random data gives you just massaged random data. And so collisions will be nicely distributed and everything will work out. The problem with this, of course, is that it is absolute nonsense. It's just not true, right? The items that you're storing in the hash table are not random. And I want to give one concrete real-world example of this. So a couple of colleagues of mine, Mihai Petrashku and Mikkel Thorup, who've done a lot of fairly recent work in hashing, worked at AT&T until very recently. And one of the jobs that they had in AT&T was playing with the software in the routers in the backbone of the internet. Okay, so a packet comes from Uzbekistan across the Atlantic Ocean, enters the United States, and wants to get to my computer. The routers need to be able to look at that packet and say, "Oh, you need to go over there to the next device on the chain," and it needs to be able to do this in small numbers of milliseconds, because there are a few billion of these packets coming across every second. There's lots of parallelism, and it comes out to about milliseconds. And one of the primary pieces of that routing software is a hash table that takes in some sort of destination IP address and returns out of the hash table the next link in the routing chain. Now the problem is that not all packets coming across the backbone are in fact valid packets. People send garbage down the backbone all the time, usually somewhat unintentionally, but the hash function still has to be able to deal with it, and you have to be able to deal with it in a way that's guaranteed to be quick, because you don't want to accidentally send a bad packet through the router and have the internet go down. More importantly, there are people whose job it is to try to take down the internet. And they will send packets to the router hoping to find collisions in the hash table. And when they notice that certain packets are processed more or less quickly than others, they will then send a few billion of that packet to the router in an attempt to take down the backbone. And so you need extremely strong mathematical guarantees that the probability of this happening is extremely low, and even if it does happen, it's a very transient bad event that's going to be corrected quickly. Right? And this is a case where the data coming into the router is explicitly not random. This is somebody attacking the router, trying to kill it by observing the timing behavior of the data structures inside. Okay? Now, if all you're doing is writing a compiler, and you need a function that says, okay, when I see foo, that I should just think of that as variable 5, and when I see bar, I should just think of that as variable 12. And you have some hash function that maps identifiers onto place addresses in some table that you store values, it's really not as important to avoid to play these kinds of very formal mathematical games. But under certain circumstances, it's actually really crucial that you understand the mathematics behind what's going on. Okay? So, if the items that you're storing are not random but malicious, the only way to avoid having the adversary who's sending you the data figure out how you're going to behave when you get that data is to behave randomly. Okay? So this is very much in the same vein as quicksort. If you implement a deterministic quicksort algorithm, I can probably generate a long array that would take you quadratic time to sort, no matter how sophisticated your deterministic heuristic is. But if you do things randomly, the probability that I can force you to run in quadratic time is so small as it's more likely that the computer is going to explode. Okay? So the same thing here. The hash function must be random. Otherwise, you cannot guarantee anything. Okay? So if you go back to your 1970s data structure book, or say Knuth, The Art of Computer Programming, and it says, you should use the following hash function with this constant. Knuth's a smart guy. He did a lot of things for the field. This was not one of them. Okay? It was really a bad idea. Okay? Now, often when you're dealing with, so this is the sort of first order attack at what hashing is, which is I need to somehow choose a random function from the universe into the addresses in my table. And so often the simplest assumption is that h is an ideal random function, meaning I literally choose h uniformly at random from the set of all possible functions from the universe to my table. Which is equivalent to saying, every time I discover a new item in my universe that I want to store, I roll an m-sided die, and that is my hash function. Now, there's a serious problem with that, which is the second time I see the same item, I need to be able to generate the same hash value. And I could do that, in principle, by having a data structure where I access it by storing the item, and I look up with the item, and I retrieve the random hash value that I used the first time. It's just a memoization. The only problem is that data structure that I just described is called a hash table. So unless you actually want, you get stuck in this recursive loop. It's just, you can't actually have an ideal random hash function. You have to come up with a hash function that you can really compute in a reasonable amount of time. Which means, right, so reality, h is only somewhat random. And now, in order to actually talk about any kind of guarantees, I have to be able to say what I mean by h is only slightly random. Random enough that I can guarantee a low probability of collisions, but not so random that it's difficult to compute the hash function. Okay? And now we're really getting into the heart of the matter. How do you design hash functions so that on the one hand you can compute them quickly, and on the other hand they have strong enough guarantees that you know that your data structure is going to be fast. Okay? And on top of just the hash functions, which hash functions you use, also different hash functions will be suitable for different strategies for resolving collisions. Okay? So, before I talk about any sort of specific hash functions, let me describe a few assumptions that one might observe in a really careful analysis of hashing. One of them you can think of. What property do I want my hash functions to have? Yeah.
The range of the hash function is 0 to n minus 1.
That's correct.
And you have the least conditions you want the hash function to give out these numbers with equal probability.
Okay, so this is the first thing that everyone thinks of, is that you want your hash function to be uniform. Okay, so for all x in my universe and for all I in the range of indices of my table. So I'm going to use this bracket notation. This is not the 0 or 1 because that's not a Boolean inside, that's an integer inside. This is Bourbaki's set of m minus 1 of m things. This is the set of size m. I'm just going to call it 0 through m minus 1. Okay, so for all items in my universe and for all addresses in my hash table, I want the probability that h of x equal I to be 1 over m. So every hash value should be equally likely. Now, I have to be very careful here to say that this probability is over my choice of hash function. It is not a probabilistic statement about x. It is not a probabilistic statement about I. I get to pick x, I get to pick y, then you get to pick the hash function. Or you pick a hash function, then I pick x and I pick y. Okay? Really what this means is I'm imagining that I have a set of hash functions off to the side, and I'm going to pick one of the functions out of that small set uniformly at random, and that random choice is going to be what drives this probability. Now this is great for intuition, but there's a problem with it. And to show you the problem, I'm going to describe a set of hash functions that is perfectly uniform and also utterly useless. Okay? So let's start with this. For any index A in my table, let me define the function const sub A of x to be A, no matter what x is. Okay? And now I'm going to let my family of hash functions be the set of all functions const sub A, where A is in an index in the table. This set of hash functions is uniform. Now, what does this actually mean? So I'm going to have a hash table of size 100 somewhere in my program. So at the very beginning of time, I roll a 100-sided die, comes up 42. Anytime you want to hash something, it goes in slot 42. This is uniform, because every item is equally likely to land in any particular spot, because at the beginning of time, I generated the hash address uniformly at random. Right? Now, this is something a little bit weird to wrap your head around. Why on earth would anyone actually do this? And the reason why someone would actually do this is to point out that uniformity is in fact not what you want. When you motivated uniformity, you actually said what you really wanted. You said, in order to keep the probability of a collision small, I want to make the addresses uniform. But making the addresses uniform does not, in fact, keep the probability of a collision small. Here is a uniform family of hash functions where the probability of a collision is 1. Everything collides, but nonetheless it satisfies this condition that every hash value is equally likely. So what you actually want is something called universality. So for all items x not equal to y, both of these in the universe, I want the probability that h of x is equal to h of y to be at most 1 over m. And again, this probability is over my random choice of hash function in some family. And then I say this family of hash functions is universal if, after choosing a little h out of that family of functions, this probability statement is true for every x and for every y that are not equal to each other. Again, x and y are not chosen randomly. This has to hold for all x and for all y, except, clearly if x and y are the same, then h of x equals h of y with probability 1. Right? That's why that not equals has to be there. Okay. So this is sort of the zeroth. This is sort of the weakest reasonable assumption about what hash functions need to be. Okay. Now, it actually turns out they don't really need to be universal. It's okay to be what's called near universal, where near universal, you're not quite, the probability of a collision isn't quite what you would get from an ideal random function. Maybe it's a factor 2 or factor 3 bigger. This integer 2 is not particularly important. But it's okay to have a hash function where the collision probability is close to what it would be for an ideal random function. Okay. Now, there are stronger statements that you can make. For example, you can talk about what's called strongly universal. And here, strongly universal means that if I have two values x and y and two hash addresses I and j, I want this to be at most 1 over m squared. This is essentially saying something about pairwise independence. It's exactly the same notion of pairwise independence that we were talking about earlier with indicator variables. Knowing something about the hash value of I doesn't give you any information about the hash value of j. And moreover, both of those are uniform. And then you can also think about, larger versions of this where, strongly 10 universal, you would say the probability of these 10 items landing in these 10 addresses is always at most 1 over n to the 10th. I won't talk about that much in more detail, but some of the hashing strategies that people regularly use actually require these kinds of stronger assumptions in order to guarantee good performance. Okay. I'm going to stick to universal and near universal, partly because for the kinds of collision strategies that I'm going to talk about today, that's enough, and partly because I can actually describe hash functions that satisfy this condition. Okay. So, I mentioned briefly a couple of different ways of dealing with collisions. There was a hand up, yes.
So when you define this universal, the universalities, you said it's less than or equal to 1 over m.
That's right.
How can it be less than?
Oh, that's a great question. And the only way that I can convince you that this is possible is to say, in the notes, I have an explicit example, which I'm not going to go through the example. I'm going to go through the family of hash functions that's near universal. That is actually universal. And I literally just write out all the possibilities, and I observe that even though the size of the hash table is 3, the probability of a collision is only 1/5. So it is actually possible to do better. There's some weird, I don't really have any intuition here about why this doesn't violate the pigeonhole principle. But in fact, it doesn't. Right? It's something about, the way things are clustered, round off errors, that you can actually do very slightly better than 1 over m. Not enough better than 1 over m to really worry about. This is not going to have any undesirable side effects, but in fact, that less than or equal to is correct. Okay. All right. So I mentioned there were a couple of different ways to resolve collisions. One of them is to say what's called chaining. Is to say, okay, here's my hash table. But I'm not just going to store one item in each of the spots in this table. Instead, I'm going to have attached to every item in this array a secondary data structure where, here's index I, and what I'm going to store in here is everything that whose hash value is I. That I've seen in the, all the items in my data set whose hash value is I, I'm going to stick into the secondary data structure. Now, under most circumstances, the number of items that you're storing in the table is not going to be significantly larger than the table size itself, in which case, as I'll show you, the expected size of these secondary data structures is constant, and then it really doesn't matter what the secondary data structure is. But there are applications of hashing where it actually matters. So distributed computing is a good one. I will need to distribute my billions of web pages onto thousands of servers to index them. That means every server is going to get millions of web pages that it needs to index. And those things need to be organized in something a little bit more intelligent than a singly linked list. Okay. But for purposes of simple analysis, I'm just going to assume that, in fact, for now, this is just a simple linked list. Okay? It just, when you get something new, you glue it onto the top. When you search, you have to just traverse the entire list. I do want to point out one seeming coincidence with another data structure that hopefully you're familiar with. If I draw the data structure this way, what is it? I heard somebody say it. It's an adjacency list. But if you draw the data structure this way, it's a hash table. Obviously, it's the same thing. Obviously, in fact, the same arguments about what the secondary data structures need to be applied both to graphs and to hash tables. It just turns out that for graphs, for most algorithms, it's good enough to have a singly linked list. The more complicated, if you really are doing more advanced algorithms, you might want to put a more interesting data structure there. There's another reason why the secondary data structure is always a linked list. Anyone want to guess? It's easy to implement. But I will point out that there's another data structure that's easy to implement because you're already implementing it. A hash table. Right? And chances are pretty good that by the time you're implementing a hash table, you can probably also implement, I don't know, a binary search tree. Right? So yeah, it's easy to implement, but if you do something recursive, arguably that's even less code that you would have to write. You do have to worry a little bit about the parameters that you don't recurse infinitely, but that's not too hard to deal with. So that's not really a compelling reason. And keep in mind that what you're storing here is a data structure that answers membership queries for a set. And a linked list is possibly the worst data structure you can imagine for solving that problem. So why is it the one that everybody uses? Okay, so I mentioned this earlier, that in lots of applications of this, it doesn't matter because the length of this thing is only 5. But there's another reason. The elements don't have to be comparable, but you can always impose an order. They're represented by strings of bits, so you can just pretend that they're integers for purposes of searching.
You don't actually know the size.
Okay, so this is a good one. You don't know the size of this list in advance. So you need a data structure that you can quickly expand if you insert new items. But again, binary search trees work pretty well for this. And there's a simple dodge for hash tables for growing them, which is when the table is 3/4 full, you make a new table twice as big. And in practice, this is invisible. It's just as if you created the big table from the beginning.
The first time it was implemented, they used single.
Perfect. The reason everybody uses linked lists in their hash tables is because CLRS has a picture of a hash table that has a linked list in it. And why does CLRS use it that way? Because when Tom Corman took algorithms, he took it from somebody who's Aho, Hopcroft, and Ullman. And Aho, Hopcroft, and Ullman, they say, use a linked list. And why did Aho, Hopcroft, and Ullman do it? Because Ullman was at Stanford studying with Don Knuth, and Don Knuth said you should use a linked list. And why did Don Knuth use a linked list? Because the guy at IBM who came up with hashing used a linked list. People use linked lists because it's always been done that way. Tradition. It's a terrible reason. If you're going to do it, at least know why you're doing it. Don't just automatically knee-jerk your way to a linked list. Okay. So, but let me point out, in the perhaps the simplest use case, why this is okay. All right. So let me define. That's not what I wanted. Let me define L of x. This is the length of x's chain. And the reason it's called chaining is because this is the linked list. This is just the number of things that hash to the same place that x hashes. Okay. And so if I want to look up x in the hash table, this is essentially going to be the running time. Because I'll hash x, and then I'll run down the linked list, and either I'll find x or I won't. Okay. In particular, let me assume for the moment that x is not in the hash table, because the analysis is cleaner that way. Okay, so I can also write this as the sum over all elements y in my table of the event, 0 if they don't collide, 1 if they do. All right, so something ends up in the same chain as x if and only if it has the same hash value as x. Right? So if I want to know the expected length of the hash table, then, by the usual analysis of expectations of things that are sums of indicator variables, this is the same as the sum of the probabilities of a collision. And this is the number of items in the hash table divided by the probability of a collision. And again, it's interesting, less than or equal to. Okay. So n here is the number of items that I'm storing. M is the size of the primary table. This is often called the load factor of the table, and as long as that load factor is a small constant, the expected length of these chains is a small constant, and so the expected running time of any particular search for x is a small constant. Okay. You get slightly better behavior using other data structures besides linked lists when this fraction is big. But when the fraction is just a constant, we're actually done. Okay? So this is assuming universal hashing. Okay? If I assume near universal hashing here, there might be a factor of 2 creeping in. So the more play that you give in the definition of near universal, the slower your expected, the worse your guarantee on the expected running time is. Okay. So the next question is, how do I get a universal hash function? Okay, everybody understands the basics here, I hope. All right. So the question is, how do I define universal hashing? So I'm going to describe 2 different schemes, or let's say 2 different kinds of schemes, really 3. I'm only going to analyze one of them. I'm going to analyze the one that's easier to analyze. I'm going to describe the one that's easier to implement. So the one that's easier to analyze is called multiplicative hashing. And the idea is that my hash function, every function in my family comes with 2 parameters, a and b, which I'll scope out in a second. And the definition of the function is ax plus b mod p mod m, where that p is a prime number bigger than the size of my universe. So if I know, for example, that I'm hashing 32-bit integers, I just need to find a single prime number bigger than 2 to the 32. Right? A has to be between 1 and p minus 1. B has to be between 0 and p minus 1. I'll write this more simply as A has to be in the set of all integers between 0 and p minus 1 except 0. That's what the little plus means. And B has to be in the set of integers from 0 to p minus 1. A and B, these are called the salt of the hash function. And then the idea is that I'm going to define this family of hash functions H, which is the set of all functions a comma b, where a and b satisfy these constraints. Okay, so this is p times p minus 1 different functions. I'm going to, at the beginning of time when I create the hash table, I'm going to roll a p-sided die and call that b. I'm going to roll a p minus 1-sided die and call that a. And I'm going to use those 2 randomly chosen values, a and b, for the lifetime of the hash table. So the randomness is all at the very beginning when I initialize the data structure. After that point, I've chosen my a and b, which means I've chosen my hash function. Everything else is deterministic. Okay. The fact, I mean, this is a bizarre looking thing, but the fact that I'm using a prime number there, the reason for that is I'm going to be relying on an interesting fact from number theory, which is that modular arithmetic works completely mod prime numbers the way that you normally think of arithmetic working. So modular arithmetic on the clock over there, that's mod 60. I can add, I can subtract, it all makes sense. I can multiply, it makes some sense. I just take the remainder divided after I divide by 60 when I'm done. But division is a bit weird. Division relies on the fact that I have multiplicative inverses. For any number A in my set, there's another number B such that A times B is equal to 1. And for 60, there's nothing I can multiply 4 by that will give me 1 mod 60. Okay? But when I have a prime, right, so if prime P implies for any integer A, except of course 0, there is a unique integer Z, also not 0, such that A times Z mod P is equal to 1. There's a 5-line proof of this in the notes, but I just want to move on. What this means is that I can do arithmetic mod P, including division, and it will work the way you expect arithmetic to work. Okay? All right. So I want to claim now this set H is universal. Right? Now, hopefully it's clear that aside from choosing that enormous prime P, which is a little bit complicated, this is something that you can implement in a few minutes, or possibly even in a few seconds. Yeah?
Just a question on notation. What is the bracket, plus?
This is here. So bracket P means the integers from 0 to P minus 1. And the plus just means except 0. Yeah.
So here, if I actually have an input that is uniform distributed, and after I do the multiplications and the addition, I could imagine that this is still uniformly distributed.
Yes.
But if I do the mode, I'm wondering if this is actually not going to be the
Hence the less than or equal to 1 over m. You're right, because so the question is, what you might imagine, for example, is if I pick random values of x and I do the ax plus b mod p part of this function, the output of that part of the hash function is still going to be nicely uniformly distributed across the size of the universe, or really across the size of the integers mod p. But when I fold everything down mod m, I'm going to create some collisions, and because p is not a multiple of m, p is a prime number, some values in the table are going to be more likely to get collisions than others. The flip side of this is p is bigger than the size of the universe. So even if I hash everything in the universe, when I do that ax plus b mod p, I'm actually opening up some gaps. And when I fold back down, those gaps actually coincide with the places where you fold over too much with the round off errors between p and m. Right? At least that's some bit of intuition, I think. Again, this is in fact the example that I work out with p equals 5 and m equals 4, and it actually works. Okay? I just write out all possibilities, and you can just count. Okay, so let me quickly walk through a sketch of a proof for why H is universal. Okay, I'm not going to go through this in explicit detail, but I want to give you a sense of what's going on. So the first thing to notice is that if I have two items, I'm just going to fix two items at the beginning that are not different. They're not the same. And one of the consequences of p being prime is that ax plus b is not going to be equal to ay plus b, even after taking this mod. This is a consequence of p being prime and p being bigger than the size of my universe. So the first part of the hash function, ax plus b mod p, that part doesn't introduce any collisions at all. Okay. Now, let me go further and fix two possible values, r and s, and ask, what is the, what can I learn from, ay plus b is equivalent to s mod p. This system of equations. So I've fixed x and y, and I've fixed r and s. This is a system of two linear equations in two unknowns, a and b. And so, because I'm working over primes, arithmetic works the way I expect. In particular, that means linear algebra works the way that I expect. This system has a unique solution. AB, where in fact A happens to be a non-zero number and B can be anything between 0 and p minus 1. Okay? And so if I imagine generating A and B at random, and asking what's the probability that this both of these equations hold, this is going to be 1 over p times p minus 1. I have p possible choices for B, and I have p minus 1 possible choices for A. Okay? So this is not asking about the probability of a collision, but it's asking about the probability of this partial hash function sending x to a particular number r and sending y to another particular number s. Right. And now I can conclude from this the probability, again over my random choices A and B, that x and y are actually going to collide. This is going to be some number n over p times p minus 1, where n is the number of pairs AB. N is the number of pairs RS such that R mod M equals S mod M. So the first part of the hash function maps to these two numbers between 0 and p minus 1. And then when I take the mod M, I do this folding, and what I'm really asking for is that last folding step. How many different pairs would give me a collision? And a little bit of math here implies that, well, I have p possible values of r, and for each possible value of r, I've got at most p over m with a floor, different values of s that would give me a collision. This is at most p times p minus 1 over m. And so if I plug that up here, I get at most 1 over m, which is what I was hoping for. Okay. If that went by a little fast, don't worry about it. The intuition that I want to get across is that the universality of this particular set of hash functions is really just a consequence of modular arithmetic behaving nicely when the modulus is a prime. Okay. So, as I said, hopefully this is something you can implement reasonably quickly, except for that nasty problem of choosing a large prime number. Right? If you've ever taken a crypto class or taken a number theory class, you might have heard that discovering large prime numbers and actually proving that they're prime Yeah, in principle you can do this in polynomial time, but in practice it's actually a bit bothersome. It's a bit impractical. In practice, it's enough to generate a large prime number generate a large number at random and do a few spot checks to make sure that it's not obviously composite. But that's not unless you really want. If you really want mathematical guarantees, you really do need that to be a prime number. Fortunately, there is an easier hash function. It doesn't look easy the first time I write this down, but let me just start writing this down. Okay, so let me assume that my universe is the set of words that I might, I'm going to use W to be the length of a word in my machine. And the items that I am hashing are words. Each word is W bits long. And so the possible words are the integers between 0 and 2 to the W minus 1. Okay. Let me also assume that the size of my hash table is also a power of 2. It is as simple, especially when you're doing dynamic hashing where you're inserting new things. When the table gets full, you double it in size. Naturally, you're going to end up with something whose size is a power of 2. Data structures whose sizes are power of 2 line up nicely with cache lines and page boundaries and things like that, especially if you're allocating them dynamically. So there are other systems level reasons why you would want to do this. So it's kind of convenient. And then let me imagine that I'm going to pick an odd integer a out of my universe. Okay. Then I'm going to define my function h sub a of x to be this weird looking thing. A dot x, that's just multiplication, mod 2 to the w over 2 to the w minus l, floor. Okay, now looks really horrible. But now let me write it out differently. Okay, so there are two parameters, a and x. A is the salt, the random thing that I'm going to choose at the beginning, just guaranteeing that it's odd. And x is the item in the universe that I want to hash. What I'm going to write is a star x. And then I'm going to downshift that by the word size minus the number of bits I need for an address. Okay. If I want to think of this in pictures, what I should imagine is, here's x and here's a as two w-bit integers. When I multiply them together, I get ax. This is a 2w-bit integer. So this is w, this is 2w. And then the hash value that I'm going to pull out are these L bits. This is h sub a of x. Okay? There is the one-line implementation. It's not even a function call. It's just a macro. I need to define I need to make sure that I have variables w and l that are easily accessible, but that's about it. And now this family of all of these so-called binary multiplicative hashing functions. So h sub a, where a is in the universe and a is odd, is near universal. Okay, here the collision probability isn't 1 over m, it's 2 over m, and intuitively the reason it's 2 over m is because I'm only allowing myself half of the possible salts, but the even numbers kind of screw this up a bit, because when you multiply by an even number a, then you know that the least significant bits down here are going to be zeros, and that's bad. Okay. So if you're going to implement a simple hashing function, This seems pretty good. Right. This, by the way, was proved in 1997. Not terribly long ago. And it shows how old I am that I think of 1997 as not terribly long ago. Most of this stuff about hashing, the original development of hash tables happened in the mid-1950s. The multiplicative hashing that you saw back here, that was first proposed in the early 1970s, and that was sort of the sort of one of the gold standards for many years. People had actually used this bitwise multiplicative hashing before, and gee, it worked pretty well in practice. But it was only relatively recently that people were actually able to prove why it was good. And the proof is a page in the notes. It's slightly more complicated case analysis than the one I just showed you. Yeah.
What's the bottom right?
I'm sorry?
What's the bottom?
I'm multiplying a number that's about 2 to the w by another number that's about 2 to the w, so the product is going to be about 4 to the w. I need twice as many bits to store to exactly store the product. Now, in practice, of course, I only need the bottom word here. And so if you do a single precision multiplication and you throw away the overflow, you're doing the right thing. Which is why there's no typecasting in that C code. Yeah?
Do you need a mask key or micro?
No. That's why I did that automatically. I'm doing, whatever the precision A and X are, the multiplication only works to that precision. And so I'm automatically masking out the high order bits, and then the shift masks out the low order bits. Okay. So far so good. We've got a near universal set of hash functions that we can use that are simple and provably work. We have a mechanism for under the assumption that the hash function is near universal, guarantees that the time to search for any particular item is going to be only a constant. But still, this is not quite what we want, because it still allows for the possibility that no matter which hash function I pick and no matter how I resolve collisions, after I build my hash table, one of the chains will be really long. And someone watching the memory of my machine might notice that if I can aim for this cell of the hash table, I can get really bad performance. Okay? So what I really want to be able to say is something of the following form. For any set of items, if I choose H from some universal family, and then I build a hash table, then I know that the expected value of the maximum length is only going to be constant. And it's really not the maximum length, it's really the maximum time I need to search for something that I really care about. Okay? This is what I would like to be able to claim, and I can't claim it at the moment. Right? And one of the reasons I can't claim it is, in fact, I couldn't claim this even in the simplest possible case, where the number of items I'm hashing is equal to the number of cells in the table. Okay, so even if m equals n, and even if I'm using an ideal random hash function, the maximum size of this is going to be about log n over log n with high probability. So if I literally just line up 100 boxes along this table, and I take 100 ping pong balls and I throw them randomly into the boxes, I'm not going to get one ping pong ball in each box. I'm going to get actually something like one of these boxes is going to have about 5 ping pong balls in it. Almost sure. Okay. This is the weird intuition about what it means to be uniformly at random. Uniformly at random means everybody is equally likely to be chosen by each particular item. But when I throw things uniformly at random into my hash table, which is what an ideal random hash function would do, there's going to be clumping. There will be some parts of the table that are empty and some parts of the table that have fairly big chains. This, by the way, gets even worse if the only thing I can assume is universality. This can potentially go up to something like square root of n. Okay. On the other hand, if the size of my table is about the square of the number of items, if I increase the space a lot, I'm sorry, there was a question back here.
What do you mean by WH?
With high probability. With probability 1 minus 1 over n to the 10th for arbitrary values of 10. That depend on whatever that 10 is. Right? Okay. On the other hand, if m equals n squared, and even if I just have universal hashing, the probability that there are no collisions at all turns out to be at least 1/2. So in principle, what I could do if I really want to guarantee expected worst case behavior that's just a constant is I can just make my tables really big. Right? And if I make the table the square, if I'm storing 1,000 things, I just build a table of size 1 million, then at least half the time nothing is going to collide at all, even under the weakest reasonable assumption for random hashing. Also under the strongest reasonable assumption for random hashing, you can't actually do much better than this. Which means half the time hashing is absolutely perfect. If I happen to discover that hashing is not perfect, I say, oh well, I throw the hash table away and I do another one. And after, in expectation, 2 rounds of throwing things away, I'll have discovered a perfect hash function. Okay? But that's bad. I don't want to spend quadratic space on a hash table that's just answering yes-no queries. So what you can do instead is use something that is somewhat inappropriately called perfect hashing. And the idea is I'm going to use chaining. For each item I, let me write n sub I to be the size of the number of items hashing to slot I. Here I'm going to build a hash table of size n sub I squared. So my primary data structure is a chained hash table. And for each of my chains, I'm going to build a secondary hash table whose size is the square of the number of things that would fall into that chain. Okay, so again, I should have the arrows looking like this. Now, this looks like it should still be bad, right? But in fact, it turns out that the expected value of n sub I squared, sorry, I should be a little bit careful here. The size of this hash table is the sum over all I of n sub I squared. Okay? So this is the same as the sum over all I of the expected value of n sub I squared by linearity of expectation. This turns out to be at most 2n minus 1. And the details of the analysis look very, very similar. It's another 6 lines of algebra, or maybe 7 lines of algebra, which I don't want to do, especially because I only have 2 minutes. But ultimately, this is going to, essentially it's the same kind of algebra that I didn't give you when we talked about Chebyshev's inequality. I just very carefully write down what's the probability, I express n sub I squared. I express n sub I as the sum of indicator variables. I expand the summation. I apply the definition of universality at one point to get rid of part of the sum. And this all collapses down to something of linear size. Right. So what I end up with is a data structure that uses only a linear amount of space, where the expected maximum time to look up anything is only constant. Because how do you look something up in this data structure? You compute the primary hash function, you indirect. You compute the secondary hash function, you indirect, and you're done. Okay. And so this, finally, is a real hash table. With all the, I've hidden some of the mathematics of the analysis, but this is how you get a hash function that you can compute in constant time, and you build a data structure where you can guarantee that even after you've built the data structure, if an adversary looks at the worst possible query, in expectation that worst possible query is only going to take you 2 table lookups. And the size, I should say, actually, if I'm really being careful about this, I should say it the following way. The space is actually what I'm randomizing here, not the time. The time is always going to be constant. But the space is not going to be too big. Is there any questions about this? So next time I will tell you about open address hashing, which is the other way of resolving collisions. One of the bad things about using chaining, even with a scheme like this, is that it requires dynamic memory allocation. There's a little bit of fragmentation of the data. There are some unfortunate cache effects. There are a number of reasons why you might prefer just to have a contiguous block of memory as your data structure. Open addressing allows you to do that. And it turns out even under those, you need slightly stronger assumptions, but you can still get good performance guaranteed. Okay. Thanks, and we'll see you on Thursday.